All right, I think it's about 5 after the hour, so we ought to get started. Before we forge bravely ahead, I'd like to make sure that everybody has a copy of the things that we've been handing out. There's a copy of handwritten notes on the derivation of the 17 plane groups. Need a copy of that? Thanks. There you go. And then there is, in addition, a set of diagrams from the international tables that give very nice pictures of all of the plane groups and the arrangement of symmetry elements. That's the only other thing that was handed out up to this point. All right, then for your continued edification and amusement, I have another problem set. And let me say something about this problem set. The first problem gives you some angles between crystal faces and asks you to deduce a possible set of lattice translations which are consistent with those angles. And in the days before diffraction, that was what crystallography was all about. It really was mapping the geometry of crystals. And the interesting thing is you could measure these angles very precisely with a device called a reflecting goniometer. Provided you had a crystal with nice shiny faces on it, you had a two-circle instrument and you could adjust the crystal so that a light beam, a very finely collimated beam of light, was focused into an eyepiece. And you could measure angles to within not 1 minute, but 1 second of arc. And from this you could deduce, if you could assign Miller indices to the faces, you could deduce not the absolute magnitudes of translations, but you could deduce the ratio of them. And along came X-ray diffraction and shook everything up. Turns out sometimes you were right and other times you were wrong because you had determined a self-consistent set of indices but not the ones that were correct. So this is to give you a little look at the early days of crystallography and to see if, using the way Miller indices are defined, you can calculate a ratio of axes. Not terribly demanding, but worth doing. Then we had talked earlier about these combinations of symmetry elements as constituting the elements of a group. And in the second problem, I asked you to take a not trivially simple, but a fairly complex point group 4mm and show that indeed the operations that are present satisfy the group postulates. And that is worth doing once so that you convince yourself these really are groups. And then the third problem is easy to state, and it is diabolically tricky. So I'll let you have a go at it, but don't beat your brains against your desktop for an entire evening over it. Try it. If you don't see the solution to it, all will be revealed later on in class. But it's based on the fact that the plane groups, which we've now derived, 17 of them, these can be viewed as the base level of a three-dimensional space group. And for each of them, you could take another translation, T3, that was perpendicular to the plane of the group, and just imagine all of those rotation axes and all of those mirror planes not being two-dimensional operations, but three-dimensional operations. The only one where you could pick the translation generally would be the oblique lattice P1, no symmetry at all, and there you could pick the translation in any orientation you wished. But for each one of the 17 two-dimensional plane groups, there is a corresponding three-dimensional space group. So we've got 17 three-dimensional symmetries for free without really doing any additional work. However, there's one thing that one should not gloss over. We found that a rotation point in a two-dimensional plane allowed only a very limited number of lattices. But we were not thinking of things in terms of 3 dimensions. So what I'm inviting you to do in the third problem is to consider now that construction that we did where we showed that rotation angles were restricted to values of cosine of alpha equals 1 minus p over 2. Now generalize that to a 3-dimensional situation where the translation does not have to be perpendicular to the rotation axis, but can be inclined to it. Are there additional rotation axes allowed? Are there fewer? Something we ought to examine. But there's a little bit of ingenuity that you have to use in that proof, but I invite you to have a go at it on your own. So with that tantalizing introduction that we'll want to send you running home and start it as soon as we finish our class this afternoon, let me hand out, without any further blather, problem set number 5. Pass that in the back corner. All right, last time, without saying much about them, I handed out this extract from the international tables that summarized the 17 two-dimensional plane groups and their properties. And I'd like to spend a few minutes going over the considerable information that's contained on these pages. Each one is treated in the same way. And let me start with one that's almost trivially simple, and that's the twofold axis in the oblique net. Across the top of the page, you find in boldface the symbol for the plane group. And then, just counting in order of increasing symmetry, the number of that particular plane group in the set. And then a symbol that really has its full meaning only in 3 dimensions, but it gives the symbol for the lattice again 2 and then a 1 and a 1, which says that if this were a 3-dimensional space group, there would be a twofold axis in one direction and no symmetry at all in the other 2 directions. And then next comes the symbol for the point group of the crystal. And we derive this particular group by dropping point group 2 into a lattice. And then the coordinate system that is necessary to describe the features of this plane group if you take the edges of the unit cell as the basis of a coordinate system. So this is something called a crystal system. So for each of the plane groups, you have this information spread across the top of the page. And then underneath that is a diagram that, by means of open circles, shows the way in which that particular symmetry moves a motif, or atoms in the case of a crystal, moves atoms around. And for P2, we have the pair of motifs of the same chirality related by a twofold axis, and that then is hung at every lattice point of an oblique net. And then immediately to the right is the arrangement of symmetry elements in the group. Then the way in which that particular plane group can move atoms around to generate a structure is summarized for you. And the first thing they have to state is where you're going to choose the origin. There is no unique lattice point. It's convenient to take the origin at a location of high symmetry, and in this case, the smart thing to do is to take the origin at one of the twofold axes. That's a non-trivial question because there are some groups that have different kinds of rotation axes. P4 has a 4-fold and the 2-fold. Taking the origin of the coordinate system at a location of high symmetry then gives you the scope of picking either a 2-fold or a 4-fold axis. Yes, sir?
On the left-hand figure, what's the, those aren't mirror planes they clearly there, are they?
On the
Parallel where you have that.
okay, here they have this, that's just to split things up into quadrants. So you have a feel for how the atoms hung at the lattice points split up into different quadrants. That is a very good point, though. Mirror planes are shown as bold lines. Sometimes the outlines of the cell look pretty bold themselves. So if you turn the page to PM, if you have the notes with you, you can see the lines that are reference lines for the cells are lighter in their weight than the symbols for the mirror planes. But it's a very subtle difference, and when you've Xeroxed it a couple of times, it becomes almost indistinguishable.
Say one more time. Origin
That's at the twofold axis. Yeah, that means that this is the location of 0, 0. And it is always assumed, but nowhere stated specifically, that the origin is in the upper left-hand corner. And what is also assumed but never stated is that the x-coordinate in the a-axis goes down and the y-coordinate in the b-axis goes from upper left to the right. That is nowhere stated anywhere in the international tables, but that is the direction that is assumed for the reference axes. Okay, so we'll take our origin of the twofold axis. That's a sensible thing to do. And then there are two ways you can look at how the particular plane group generates a pattern. You can do it with little circles or little commas or something like that. In other words, do it graphically. But a way to communicate the atomic arrangement in a structure, which is going to be the most free of ambiguity and rigorous, is to do it analytically. And that's what the tables do for you next. They give an analytic description of the way in which the symmetry elements will move an atom around. For this particular plane group, things are very simple. This is the direction of x. This is the direction of y. And if we plop one atom in here, it will be at a location x and y. So that's what happens when you drop one atom in it. That atom gets hung at every lattice point, and it gets rotated by the twofold axis. So you're going to get two of them per lattice point. That's somewhat arbitrary which pair you take. The coordinates of this atom are x and y. The coordinates of this atom inside of the box is 1 minus x and 1 minus y. That would do it. But it makes sense aesthetically and to see that the atoms are related by symmetry if instead you specify as the two atoms per cell the two that are hanging at the lattice point. And in that case, the coordinates of the first, if they are x and y, would be minus x and minus y. If you have a pair of numbers, 0.283 and 456, then minus 0.233 and minus 0.456 leaves no doubt that these are positions that are related by symmetry. If you have coordinates like 0.2, 0.3, and then 0.8, 0.7, without doing some arithmetic in your head, it's not clear that those are going to be atoms related by symmetry. So the coordinates that will be stated for you then will be the coordinate of the pair of atoms at the lattice point, and some of the coordinates would be negative. This is something called the general position. And that transformation of coordinates is different for every one of the plane groups. That's what makes them different. They're different in the way they move around an atom in a general location and fill space with it. So that's the general position, and it is unique for each plane group. And there's several ways in which this information is conveyed to you. Move this over a little bit, xy and minus xy. The first thing that's a characteristic of the position is the number per cell. So you get the number 2, or this is sometimes referred to as the rank of the position. Drop in 1, and you get a second one out related by symmetry. The next is, and I'll go to the last next, this is the site symmetry. And by definition, this is always 1, no symmetry at all, for a general position. All right, so why make a big deal about all these characteristics of the general position? The reason is that there are locations that are termed special positions. And let me clean up this right-hand part of my diagram and say that for plane group P2, you will always get 2 atoms per cell if you place an atom in an unspecialized location. Well, what would be a specialized location? Suppose we would drop the atom down right smack on top of that twofold axis. Then that twofold axis is just going to twirl the atom around on its axis, and it's not going to map it into a second location. So following the general position has always provided to you a set of special positions. And what's special about them? They are on a symmetry element. You can look at the characteristics of a special position in 2 ways, either geometrically or you can do it analytically, as I'll show you in just a moment. Imagine that the atom is to sit here. X and Y migrate progressively towards the location 0, 0. And then the other atom, related to it by twofold symmetry, will move towards it until finally the 2 of them will merge into just one single motif. Okay? So when that happens, you get not 2 per cell, you get only 1 per cell. And the reason for that is the site symmetry is 2. It's on a twofold axis. But there are other twofold axes as well. What if the atom migrated to the position 0, 1/2? If that were the case, if the representative atom moves to here, this one up here will migrate down, and the 2 will merge into one atom that sits at just 0, 1/2. Okay? So there will be another type of special position, 1 per cell, also on a twofold axis. This one was at 0, 0, and this one is at 0, 1/2. You remember we made a point of saying that there are 4 different kinds of twofold axes within this plane group. Different in how they are positioned relative to a pattern, different in that they are not mapped into one another by some other symmetry element which is present. So each of these 4 locations is a location of another general position of rank 2 sitting on a twofold axis. Let X and Y migrate down to 1/2, 0, and this one will come together. So there's another one giving you 1 per cell, sits on a twofold axis, and this would be at the location 1/2, 0. And finally, there's another one in the center of the cell, and if you let the atom migrate to that location, again, the atoms will coalesce pairwise into a single one. So there'll be another one, 1 per cell, and also on a twofold axis, and this would sit at the location 1/2, 1/2. And those, then, are the characteristics of this particular simple plane group. There's another symbol that's added, and this is something called the Wyckoff symbol. Wyckoff was a crystal chemist who attempted valiantly back in the early days of the century when there were a couple of dozen structures determined per year because it was such a grand new adventure and few people knew how to do it. But Wyckoff tried to summarize between one pair of hard covers all of the crystal structure determinations that had been performed in a single year. And he went at this courageously for perhaps a dozen years, and then results began to accumulate so rapidly, he just said, the heck with it, clapped covers on it, and that was the end of his series of books. So they don't get very far. But it was a real useful contribution at the time. This is just a shorthand way of referring to the position. And he starts with A for the most specialized, runs the way up through the alphabet until you've assigned a letter to each of the positions. And this is a nicety. All these special positions, for example, sit on a twofold axis, and you don't really have to specify the coordinates because they have to be either 0 or 1/2. So this gives us a way of saying you've got an osmium atom in position 1A, and you've got an oxygen atom in position 1C. And it's a nice shorthand way of avoiding mentioning things which can be tabulated once and for all and not stated explicitly. Okay, so this, my friends, is the language in which you will see structural data cited when people have determined using diffraction methods the locations of all of the atoms within the unit cell of a particular material. If the coordinate is variable, with today's techniques and high-speed computation, you can get x as a fraction of a cell to usually at least plus or minus 1 in the 4th place. So it's data that can be determined extremely precisely. Yes, sir?
I didn't quite get what the exact definition of the general position was. Is it a set of points related by one symmetry?
The general position, it's a set of equivalent positions that are related by symmetry. Yeah, yeah. And the general position, yeah, each of these is called a set of equivalent positions. Equivalent in the sense of being related to one another by symmetry. And the entire set is sometimes referred to as an singular equipoint. Sort of a condensed jargon for a set of equivalent positions. So when one speaks about an equipoint of rank 2 in this case, or rank 1. Let me just, even for this trivial two-dimensional symmetry, give you an example of some information that falls out of this immediately. First of all, you can use these special positions only once. If you put an atom in position 1C at 1/2 0, it's used up. You can't put another atom in there in a given structure. Secondly, if you think more globally, not in terms of atoms, which to a good approximation are spherically symmetric, but think in terms of a molecule, if you're a polymer scientist or an organic chemist, and not place an individual atom, but place an entire molecule. If there's one molecule per cell in this particular symmetry, that molecule has to sit on a twofold axis. And that means the configuration of that molecule is going to be limited to having to conform to a twofold rotational symmetry. So just from the density and the lattice constants, if you find there's one molecule per cell, you know that molecule has to have twofold rotational symmetry. So you can say something about the structure of the molecule. So there are lots of ways in which the symmetry information has something to say about the arrangement of atoms in the structure. Okay, any further questions? Yes?
How do they decide between B, C, and D which is the most special for?
That is a very good question, and the way it's decided is by you getting there first before anybody else did it. So everybody follows now the conventions that are given in the international tables. That's sort of the dictionary of all these terms. But you're absolutely right. What is more special about this one than this one? Well, they're all locations of the same symmetry. You can turn one into another by changing the origin of the cell, where you're going to define a lattice point. So they are thoroughly arbitrary. What is generally done is to take 0, 0 as for your particular choice of origin as position A. And then what should come next? 0, 1/2 or 1/2 0? The truly observant among you will notice I snuck a quick peek at the international tables before I wrote one of these down. I can never remember which is which. It is arbitrary. Usually you end up with the one that has both coordinates non-zero. But that is code that's embodied in the international tables. But that's a good question. Yes, sir?
How did you decide to make the motifs converge upon your special positions?
Oh, I just changed the value of x and y. Those are numbers that can be, for the representative atom, each of them can be between 0 and 1. So what I just said was what will happen if we let x and y take on not general values, but very special values. And the special values are going to be things like 0 and 1/2 if I have picked my origin as a twofold axis. Okay? It's another reason for picking your origin at a location of high symmetry.
But how about your other non-origins of special positions?
There are two ways you can do it. There are two ways you can do it. One of them we just did. We just looked at the geometry. And we said if this representative atom, this is the one we define as being at location x, y. If x and y both approach 0, this atom and the one over here are going to migrate towards the origin lattice point and eventually just coalesce. Okay? If I let x and y migrate, x go to 0 and y go to 1/2, then this one and this one will come together and coalesce. So that's why I did that, because I knew that the number that I would generate would be smaller than the number that I would get for a set of coordinates for an atom that was off the symmetry element. I said there's another way of doing it. For something this simple, it is not really that profound, but it is a way of checking whether you've counted the same position twice. I said you can imagine these special positions arising when x and y assume special values. So let's let, for example, x be 1/2 and y be 0, and plug those coordinates into my equation for the general positions. So I'll put in 1/2 for x, 0 for y, and then I'll put in minus 1/2 for x and minus 0 for y. But what goes on at minus 1/2 has to be the same as what goes on at plus 1/2 if the structure is based on a lattice and periodic. So what I'm really getting is 1/2 0, 1/2 0 twice, which is the same as saying if x is 1/2 and y equals 0, I'm putting two atoms together right on top of one another. So you can do it analytically. And for the more complicated symmetries where there might be 20 or 48 atoms, that's a good way to see if you've looked at the same position twice. Okay? So we're going to do a couple more before we move on. And this one is almost trivially simple. Any other questions before we go forward? Okay, let's take one that is slightly more complex. And I'll go to one of the rectangular groups. And let me look at, let's take plane group P2MM, which has got a fair amount of symmetry to it. All right, so this is the group that we got by putting 2MM into a lattice that had to be rectangular then. And across the top of the page, this is number 6. You'll see that it is rectangular. Has to have a lattice in a rectangular shape because of the symmetry. Next comes the shorthand symbol. And I always feel a little bit apologetic when I have to point out the existence of this. And the reason is that people who work with symmetry are no more or less lazy than any other human being. And some of the symbols become really ungainly when we go to three-dimensional symmetry. And something like A 2 sub 1 over A, 2 over M, 2 sub 1 over D is a mouthful. And actually, what's done is to just specify the minimum amount of information which defines the symmetry. So here, 2 m's that intersect have to give you point group 2mm. And then comes the full symbol of the plane group, P2mm. And for those who are counting, this is number 6. And the shorthand symbol is PMM, or the short symbol for the point group, along with the lattice. Is sufficient to tell you that this is 2mm placed at the nodes of a rectangular lattice. Then underneath comes the representative pattern. And again, there's a cross in the middle of this just to split it up into quadrants. The symmetry is one that we've already encountered, was fairly easy to come to terms with. Twofold axes at the corners of the cell and in the center and in the midpoint of the edges. That's just like P2, except the mirror planes that are present require that that parallelogram in P2 straighten out into a rectangle. And then we put 2mm at the lattice point, so the mirror planes run down through the cell like this, up and down, and left to right. So here's all the symmetry here. Pattern, I'll say it again, it's so easy to forget. The pattern is nothing more than the pattern that 2mm produces hung at every lattice point of a rectangular net. And all of these symmetry planes and symmetry axes that arise are just ways of defining all of the relations that exist between these things when you perform that process of addition. So this is then the arrangement of all of the atoms in the cell, and then some. And then there's a new symbol that's introduced, and somebody asked about that last time. To me, it looks like a little tadpole inside of a frog egg. Has anybody seen a frog egg? That's just what it looks like. It's a little tiny tadpole in there waiting to hatch out. So here is our little tadpole. This is used to indicate an enantiomorph. Okay? If this were a motif with chirality, this one would be right-handed, this one would be left-handed. So that indicates all of the atoms or molecules that are of the same chirality. The purists among you will notice that the dummy that produced this diagram did not show the tadpoles conforming to the twofold symmetry. Both of the commas point in the same direction. Tisk, tisk, little oversight. Okay, so this then is the arrangement of motifs in the pattern. And now let's proceed to analyze that according to the nature of the positions that are available of different sorts. Again, coordinates have meaning only if you define the origin. And nobody in their right mind would want to pick an origin that is off at least a symmetry plane, but the thing to do is to take the origin at 2mm. Okay, again, I'll remind you that x goes down this way, y goes this way. So if I have a representative atom at x, y, I'll have another one at minus x plus y, another one at minus x minus y, and one at plus x minus y. So there are the coordinates of all the symmetry-related atoms. So putting down the general position, I get 4 of them if I place one in the cell. By definition, the general position is always at a site of symmetry 1. So this is the site symmetry. And we just rattled off the coordinates. They're x, y, minus x, y, x minus y, and minus x minus y. Okay, there are lots of special positions here now because we have not only twofold axes with mirror planes intersecting at them, but there are also locations of just a mirror plane alone. And there are a total of 4 distinct independent mirror planes. This one, this one, this one, and this one. So we're going to have 4 positions where the atom sits at a location of symmetry 2 mm. And those are going to be analogous to the positions that we found for the twofold axes in P2. And not surprisingly, the coordinates look very much the same. 0, 0 puts us on a location of symmetry 2 mm. 0, 1/2 does the same. 1/2, 0, and 1/2, 1/2. So the 4 positions of symmetry 2 mm. And then there are 4 positions just on a mirror plane, but not on a twofold axis. And we could do that for the mirror plane that runs along the x-axis, or the mirror plane that runs along the direction of x at y equals 2. And the order in which you pick them is rather arbitrary, but there will be a pair of positions at x0 and minus x0. That would happen if the y-coordinate was exactly, draw what the position is just off here to the right in a small diagram. This would be where you put the atom on the mirror plane running through the origin. And these things would give you only a pair. The next one is at a position x 1/2. And that's where the mirror plane would be the mirror plane that is along the position y equals 1/2. And here we would get atoms coalescing like this. X is general, but y is exactly 1/2. So we'd have x 1/2 minus x 1/2. And I better put these off to the right here. The remaining 2 are 0, y, and 0, minus y. That is also a position of site symmetry M. And that would be a pair of objects that has x equal to 0. Y is anything, so that's this mirror plane here. And in that case, we'd have a pair of atoms left to right, reflected by the mirror plane that goes through the origin. And the last one, thank goodness, is one at a location 1/2 y and 1/2 minus y. And this would be the mirror plane exactly at 1/2. Y can be anything. So that, sorry, x is 1/2. So that would be a pair that sits somewhere on either side of the mirror plane running through the center of the cell. That's also a site of symmetry M. Now we assign the Wyckoff symbol by working our way up the alphabet. So this is A, this is B, this is C, this is D, this is E, F, this is G, this is H, and finally we end up at position I. For all of these, we get 2 atoms per cell. These have rank 2. For each of these, we get just a single atom.
Explain the 2 atoms per cell again. How do you use an atom per cell for that?
Okay. Which one would you like me to do? That last one? 1/2 y? Okay. So if x is 1/2 and y is anything, that's this locus here. And that is a mirror plane. And if we let this atom move from its location xy down to this location, the one in the lower part of the cell is going to move up, and these 2 will coalesce to a blob that sits there. So this would be site symmetry M. And instead of getting 4 per cell, I would get 2 per cell. This one and the one that's reflected across. Okay, now the other way of doing it is to not think about it at all. Say, here is xy minus xy, x minus y, minus x minus y. And then let's make one of the coordinates specialized. Let's let x be exactly 1/2. So I'll get a half y minus 1/2 y, and then I'll get 1/2 minus y and minus 1/2 minus y. Looks like 4 atoms, except if I've got one at plus 1/2, the one in the neighboring unit cell is at minus 1/2, so actually I've had the atoms coalesce pairwise because these coordinates are actually identical to saying 1/2 y plus 1/2 y, 1/2 minus y, and minus 1/2 is the same as plus 1/2 minus y. So you can do it that way. Just put in a special value for x or y, turn the crank on the general position, and you'll find you're going to get the same thing twice. Again, if we look at position A, which is 0, 0, put in 0 for x, 0 for y, then put 0, 0 for all these other 4 positions, you're going to get 0, 0, 4 different times. Okay, I'm going to do just one more, and the results are here for all of the remaining 14, so I don't think there's any need to do them all. But one of the things I would like to examine with you is a group that has a glide plane in it, and see how that changes things. Any other question on this?
Can you just go over the rank of 4? So 4.
4 means 4 per cell.
4 per cell.
Okay? And if you count them around the origin, there's 1, 2, 3, 4. If you count the number that's caught within the box, it's 1, 2, 3, 4. Okay?
That's site symmetry.
That's site symmetry 1 because 1 is no symmetry at all, and that is what's general about it. It's not sitting on a symmetry element which would then fail to reproduce it. Okay? And again, if the motif was not an atom but was a molecule, if you find only 1 molecule per cell from the density and the cell dimensions, that molecule has to have symmetry 2 mm. Because it's got to sit, if there's only 1 per cell, that set of atoms has to sit at a location that conforms to symmetry 2 mm. Okay, let us go to one more, and I'm going to take P2MG because it's one that has a glide plane in it. This is PMG for short. This is number 7. P2MG is the proper symbol, and that's point group 2mm, and again the coordinate system is rectangular. This is one that we derived last time. The arrangement of symmetry elements in this is, once again, a rectangular lattice, 2-fold axes. If we take the origin at 2, would be at the corner of the cell and in the midpoint of the edges. Then there's a glide plane passing through the 2-fold axes. And there is a mirror plane passing in between the 2-fold axes. And here's a good example of an arrangement of symmetry elements that has a mirror plane in it and then a line that it just indicates the edges of the unit cell. And can you distinguish the bold line from the light line? Barely. But the bold line is the mirror plane. And what does the arrangement of atoms look like? Okay, this is a tricky one because there are 2 different symmetry elements, a 2-fold axis, and that's going to take an atom at xy and repeat it to minus x minus y. But here now is a case where there's another symmetry element that does not intersect the first one. So that mirror plane is going to reflect this atom down here to an enantiomorph and reflect this atom down here to another enantiomorph. So if this is x and this is y, this one sits at minus x and minus y. For this atom here, y is the same as before, but if this distance is x, the distance up from the center line will be x, so this second coordinate is 1/2 minus x. I'll do that again since this is pretty small and tight. This distance is x. We reflect the atom across a mirror line at 1/4, and therefore the one towards the center of the cell sits up above the location 1/2 by the same number x. So this is 1/2 minus xy. And by the same argument, this one here is at minus y, and it sticks out beyond the position x equals 1/2 by the same amount x. So this one is 1/2 plus x minus y. Non-trivial. So if I begin to tabulate these, we've picked the origin at 2. Didn't have to do that. If you wanted to, you could take the origin at m if you wanted to. It's just switch everything by 1/4 in of the coordinate x. We found 4 per cell. The site symmetry is 1, and the atom locations were at x, y, minus x, minus y, and then we had 1/2 minus x, y, and 1/2 plus x plus y. I'm sorry, minus y. Okay, so the coordinates are getting permuted around in a very more complex fashion than just changing sign. Okay, special positions. Just as before, any of these twofold axes is going to be a site for a special position. Let x and y go to 0. This pair at the origin will coalesce, and this pair will coalesce at a point that's halfway along the cell. So there will be 2 of those, one at the origin, one in the middle of this edge, and their locations would be 0, 0, and 1/2, 0. And this is a site on a twofold axis. And we got only 2 per cell. Okay. Would this be a location for a special position, this twofold axis? It was before. Is it now? Key point is independent sites of symmetry. There's a mirror plane here. What goes on here has to be exactly the same as what goes on here. So this is not an independent special position. In the same way, there's a mirror plane, and if I let the atom migrate down to the mirror plane, I will have the mirror plane is at a location 1/4 y, and these will be on a mirror plane. 1/4 y would be a first, 3/4 minus y would be the second one that I get, and they would coalesce pairwise. Is this another mirror plane that could be regarded as an independent position? This mirror plane, again, is not independent. because it's related to the one we just considered by the twofold rotation about the center of the cell. So there's only one kind of mirror plane in the structure. But going back to the twofold axes, there is a twofold axis here. There's another one that is halfway along y. So there's another twofold axis that is independent at 0, 1/2, 1/2, 1/2. And this is the entire set. So there are 3 special positions of rank 2, 2 atoms per cell. We make the most specialized one be named A, work our way up to C, and the general position then is referred to as D. Okay, again, so what I did was to say that this mirror plane is related to this one by symmetry, and if there's something on this mirror plane as a special position, I'm automatically going to get it on the lower mirror plane. This twofold axis is the same as this one, so whatever is going on as a result of specializing the location on this twofold axis is going to be provided for me automatically at x equals 1/2 by the action of this mirror plane. There's nothing that throws this twofold axis into this one, though, so they're both independent. Now, one of the symmetry elements that I steadfastly ignored was the glide plane. What happens if I place an atom right on the glide plane? A glide plane, if I use a motif that has some handedness to it, we repeat the atom by translating half of a translation, not yet putting it down, first reflecting it across. This is an enantiomorph. Doing it again gives me an atom that's related to the first by a translation. What happens if I let the atom migrate onto the glide plane? Let this atom move down to here. Now it sits here. This one, repeated from it by glide, will migrate up to here. Nothing happens. It's just that the amount that the atom is displaced from the locus of the glide plane is different in the 2 cases, but there is no coalescence of the atoms because of this translation component to the glide plane. So a conclusion then is that glide is never a candidate location for a special position. Now, this is a good example of a case where I can check what I've done and to see if I counted the same position twice. I said that both of these locations are not special position. The mirror planes are related by symmetry. Suppose I were not clever enough to notice that. And I said, okay, there's going to be a special position, 1/4 y, 3/4 minus y. That's what happened if I use this mirror plane as a special position. What would I get if I took 3/4 y and 1/4 minus y? Looks like a different specialized position. But let me put this number into my expression that is the formula for the general position. If x is 1/4 and y is y, then this position here would be minus 1/4 and plus y. 1/2 minus x would be 1/4, and y is y. Okay, here, I got the same thing back again. And 1/2 plus x would be 3/4, and minus y is minus y. Minus 1/4 and 3/4 plus 3/4 are the same thing. So what I've gotten is the position 1/4 y and 3/4 minus y twice. Okay, so what this is telling me analytically, if I just plug in the coordinates of what seem to be a distinct special position, is I get the same atom on top of itself twice. And it looks exactly like choosing the first mirror plane. So that's a good way of checking, particularly in a very high symmetry where there are all sorts of sites of possible point groups that could cause coalescence, to just crank out the coordinates and see if, in fact, you've got exactly the same pair with the same coordinates that correspond exactly to the x and y of some previous location that you identified. Right, I think hopefully you have a feeling for how it works. If you look at some of the higher symmetries, the number of atoms that constitute the full equipoint set of equivalent positions for P6MM, there are 12 locations in the general position. And because the coordinate system is oblique, x and y get permuted into linear combinations of one another. So that's really extremely complicated. If you look at some of the square symmetries, the number of special positions is very, very high. There are 2 positions in P4MM. There are 2 positions of rank 1. There is a position of rank 2 that sits on 2MM, 3 different mirror planes, and the general position with rank 8 requires working your way all the way through G in the alphabet. Yes?
How do you know where to count, whether they're at the edges of the cell or inside?
Okay, for P2GG, the only site of point symmetry is a twofold axis. Okay, so the only thing that you could use for a special position in P2GG is a twofold axis. And there are 2 different twofold axes. They relate in a curious way because of the glide plane. And this is a case where the site of a special position is not related by rotation or reflection, but by a glide. P2GG looks like this. Twofold axes in the old familiar places, 0, 1, 1/2. The glide planes are here, 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 and here. So which twofold axes are equivalent? The glide would take this twofold axis, reflect it down, and slide it over to here. So whatever goes on here goes on at this twofold axis.
Sorry, I guess my question was, can you put the glide planes at the edges of the cells? Of the units that would that still be right? Or
You could, but you would lose then the apparent similarity in coordinates, in that if you put the glide plane at the twofold axis, if this is x, y, this one over here is at minus x minus y. And then if you repeat it by glide, that would slide over to here and then be reflected down here. So there'd be 1 pair up here, 1 pair down here of opposite-handedness. Okay, so you would not see the similarity. Whoops, I'm sorry. This. No, that's right. You know, if you took the origin at the glide plane, you would not see the simple relation between the numbers that you do when there is a rotation axis or a mirror plane. But you can take the origin anywhere you want. And the advantage of doing it at a symmetry element is then the numbers that describe where the atoms sit are simple permutations of sign, or adding a half to the number of the preceding atom that was just mapped to a new location. Okay? All right, I think you're more than ready for a break. Let's resume in 10 minutes, and we'll move on to something completely different.